Hello, everyone. My name is Krishan Deo, and this is my Capstone project for the IBM Advanced Data Science Specialization via Coursera. For my project, I chose to work with Spotify Daily Global Top 200 data between 2017 and 2021. And the goal with this project was to figure out if I could train a model to effectively discriminate between top 100 and bottom 100 songs. This presentation will be split into two parts. Firstly, I will go over a stakeholder presentation that is more geared towards end users and business users. Following that, I will go over a presentation more geared towards my data science peers. On this slide, you can see the overall agenda for both presentations. Starting with the stakeholder presentation, the dataset that I used for this project was uploaded to Kaggle by an individual named Khan Bui. It contains over 1,000 constituent JSON files that contain the daily global top 200 rankings for each day between 2017 and 2021. The dataset was ranked as having a usability of 5 on Kaggle. I deliberately chose this particular dataset for two reasons. Firstly, I didn't want to choose a dataset with too high usability because in the real world, data isn't always neatly wrapped up and ready to use easily. I wanted to challenge my TL skills. Secondly, I have a strong passion and background in music, and I really wanted to practice my skill set on data in the music domain. Taking a quick look at the data contained within these JSON files, we can see some really interesting features. There are numerical features that describe a song, like acousticness and danceability, and there are more categorical features as well, like artist name, featured artist, genre, etc. For the business users, I won't go into too much technical detail on how I extracted, transformed, loaded, and manipulated the data in order to get it to usable state, but I will quickly show a screenshot of the ETL script that I wrote. In short, this script looped through all the data files for a particular year, extracted the nested JSON information, engineered additional features, created labels, and finally outputted the processed data in an easily consumable CSV format. Here's a quick glance of how that data looks after processing, and you can see the top 100 and bottom 100 labels, all the different genres sorted by popularity, artist name, additional flags, etc. In all, there were 33 features extracted and created, 14 of which were numerical, and 19 of which were categorical. Which brings us to our use case. The goal I set for success for this project was being able to train a classifier that could discriminate between top 100 and bottom 100 songs with at least 80% AUC, or area under the curve. AUC is a measure of a model's ability to discriminate between two classes while also taking into consideration any imbalance in the dataset itself, i.e., whether more of one label is present compared to another in the dataset. According to general online consensus, 80% AUC is considered excellent in terms of performance. Furthermore, I wanted to extract the feature importances for the models trained so as to generate actionable insights and inform feature selection for future iterations of the project. For purposes of the stakeholder presentation, I won't be going into the actual code, but I will summarize the overall findings. I've also included my notebooks at this link in case anyone would like to learn from my findings or my learnings in the future. In terms of model performance, I initially trained a support vector machine model using strictly the numerical features as a baseline. I used the 2017, 2019, and 2021 datasets as quick checks for similar performance across all 5 years, and they all came in around 55 to 57% AUC. Following that, I trained random forest classifiers on all 5 datasets using all 33 features. Spark's implementation of random forest was chosen because it is very efficient at handling high cardinality categorical features like artist name and genre. As you can see here, all 5 random forest models performed above the 80% AUC threshold for success. Following that, I also wanted to take a deep learning approach to this problem to further practice the learnings from the IBM Advanced Data Science Specialization. Using the feature importances extracted from the random forest models, which you'll see shortly, I trained 5 neural network perceptrons using a down-selected set of features. These models also performed above the 80% threshold, which I was very happy about. Finally, as a proof of concept that hyperparameter tuning can further push the performance of the random forest models, I trained another random forest classifier on the 2017 dataset using a different set of hyperparameters, which resulted in further increased performance as you can see here. And here is a visualization of those performance metrics across all different models and years. Now that we've seen the performance numbers, I wanted to dive into the feature importances because they are crucial in setting up the final recommendations and insights. As we can see, there are 3 features that are clearly above the rest when it comes to impact on the model: artist name, featured artist, and primary genre. Of the 33 features, 13 were selected as a final set of down-selected features for future iterations of this project using their relative feature importance values. These features are shown here in pink, and here once again. This visual gives us a look at how the top 13 features fluctuate year to year in terms of importance. It is a good indication that listeners' tastes change year to year, and those changes impact what songs will ultimately fail or succeed due to their inherent features and characteristics. As we close out this stakeholder presentation, I wanted to highlight the trends present across all 5 years within the top 3 important features I mentioned earlier: artist name, featured artist, and primary genre. The trends we see are the following. Artists and featured artists with strong branding and presence are more likely to be top 100, while songs in the pop genre are also more likely to be in the top 100. On the flip side, artists and featured artists that are relatively lesser known, i.e. with weaker branding, are less likely to be in the top 100, and songs with more niche genres are also less likely to be in the top 100. You can see that here in 2017, 2018, 2019, 2020, and 2021. Some of the other insights unearthed from analyzing these particular features were that tastes change with regards to the genres that are considered most popular year to year. For example, rap used to be second most popular to pop in 2017 and 2018, but has since been eclipsed by trap Latino in the years 2019, 2020, and 2021. To close, I wanted to highlight a few recommendations for success for all stakeholders that could stand to benefit from these findings. For sake of time, I won't read through each line item, but they are all detailed here on the slide, and I'll also be making the slide deck available on my GitHub for future reading. A couple of key overall recommendations for success that I've hinted at already would be to focus on building strong artist brands, incorporating some element of pop music into one's musical style, and finally, to collaborate with artists that have strong brand presence as well. Thank you for all your time today, everyone. Please find the links to all my presentation, my code, and other pieces of my Capstone project below, and I'm happy to connect with you on LinkedIn as well. Now on to the Data Science Peers presentation. Hello, everyone. Welcome to the Data Science Peers portion of my presentation. Here, I will be going into some more detail on the technical specifics of my Capstone project. I'll also quickly walk through my Jupyter notebooks, but because each notebook has detailed explanations of every step built in already, I will not be going into line-by-line detail. Starting with my architectural choices, to leverage our learnings from the IBM Advanced Data Science Specialization course, I chose to utilize Python 3.7 as my programming language choice, with PySpark and Keras also being my choices for machine learning and deep learning frameworks. Jupyter notebooks were used for ease of development and documentation, and finally, SweetViz was a third-party library utilized for data quality assessment and EDA. As a side note, midway through development, I did run into the issue of Python 3.7 environments being deprecated and disabled on IBM Watson Studio. This prevented me from creating any new Jupyter notebooks with more powerful environments compared to the single core 4 GB instance I was developing on. This hitch point stopped me from executing my hyperparameter tuning code, but I did manage to showcase the proof of concept of this hyperparameter tuning by training another model with a single permutation of the param grid. In terms of data quality assessment, the 5 datasets used for this project were generally in good shape once I had finished processing them. As the Kaggle rating of 5 out of 10 suggests, the format in which the data came was not the simplest and easiest to handle. It required me to develop a custom ETL script to navigate the nested one-to-many relationships in JSON in order to get the data to a state in which it was usable for modeling. With that being said, using the SweetViz library, I was able to look at all the features under a microscope to better assess their quality. Typical statistical measures like mean, standard deviation, kurtosis, and skew were looked at, along with distribution histograms and frequent values. I noticed there was some bad data that needed to be removed as well, i.e. missing artist names and genres, and I also imputed certain blank values to ensure that model training and evaluation could continue without error. Genre information was also extracted, sorted by popularity, and then replaced as opposed to keeping the default alphabetical sorting. In the end, there was a slight imbalance in label distribution, but nothing to necessarily worry about. Here is a look at the final cleansed dataset, and here we can see an example of the correlation heat maps produced by SweetViz. And here's an example of the aforementioned histograms and statistical measures describing the distributions of both labels, i.e. top 100 versus bottom 100. In this case, we're looking at the danceability feature for the 2017 dataset. As part of the ETL, EDA, and data quality assessment notebook, I also incorporated the feature engineering step because I found that I needed to make iterative changes to the script in order to get the data to a stage at which it was ready for modeling. Firstly, the creation of a top 100 and bottom 100 label. Secondly, the removal of all songs that were not released in the particular chart year. This was to ensure that songs with notable longevity weren't penalized for being on the charts too long and subsequently being classified as primarily bottom 100, despite their success. Thirdly, genre sorting by popularity instead of alphabetics. Fourth, removing records with null values in crucial key features like artist name and primary genre. Fifth, imputing values for records with null values in optional features. And finally, sixth, flags were also created for features like multi-genre, number of genres, etc. And so quickly, we'll go over my first notebook. Here you can see my ETL script, the loading of the files after processing, the installation of SweetFizz, and finally running the different instances of SweetFizz for the 5 different years. Here's 2017, 2018, and the heat maps, 2019 and the heat maps for the bottom 100, 2020 and the histogram for the danceability feature as an example, and finally 2021 as an example of how it handles categorical data in terms of frequency. Here's primary artist, featured artist, and primary genre. Moving on to the performance indicator choice, we can see that I chose OROC, or area under the curve. I chose OROC because it measures the model's ability to discriminate between 2 classes while also taking into consideration any imbalance in the dataset itself. From the table here, we can see that there is a slight imbalance in the distribution of labels, which is something OROC does a very good job at accounting for. Finally, as mentioned previously as well, feature importance was used to inform insights as well as feature selection for model improvement in future iterations. In terms of algorithm choice, SVM was used to define a baseline using strictly the numerical features within the dataset. The categorical features were excluded because their high cardinality would make it inefficient and ineffective to one-hot encode before training. There would just be too many dummy variables. Spark's implementation of random forest was used as the final model choice because of its ability to handle high cardinality data through smart metadata, while also providing a bit of a boost to performance over traditional decision tree models via ensemble methodology. Finally, a simple binary perceptron with the shown configuration was used as a deep learning alternative. An 80-20 train test split was used for model definition, and then a 70-30 split was used for final training and evaluation. Here we can see my second notebook, the model definition stage, the imports, loading in the 3 different data sets, the initial SVM baseline, training, and the values for performance. And then finally, the random forest implementation using the 80-20 split with the performance values here. And finally, a visualization of the performance values. Here we can see the model definition stage performance values visualized. Obviously, there's a notable jump from the SVM to the 80-20 RF. And finally, we can see my final notebook, the training and evaluation stage. The imports, the overall performance here for the random forest. Here we can see the definition, loading the data set, training the model, evaluating on the training set, evaluating on the test set, and finally extracting the feature importances. And the same for 2018, 2019, 20, 2021. Here we can see the hyperparameter tuning step as mentioned, and the performance increased from 86% to close to 88% here. Here was the original code that I had wanted to run, but was unable to because of the deprecation of Python 3.7, along with the param grid and all the different permutations I had planned. And here was the proof of concept as mentioned, where I took one of the permutations within the param grid and trained it on a simpler random forest model, which achieved that close to 88% performance. And here's a visualization of the feature importances. As you can see, these in pink were kept for future iterations of the project. Some insights from the feature importances, the visualization of the feature importances, and finally we get into the neural network perceptron and the performance features here for across the 5 different years with no refitting, installation of TensorFlow, definition of the different networks for all 5 years, training and evaluation for the training set and the test set from 2019, 2020, 2021, and finally a visualization of performance across the baseline, the 70-30 RF, the neural network perceptron, and the tuned RF with a final conclusion. And now we can take a look at how all the models performed throughout the course of this project. RF 80-20 refers to the model definition stage, whereas RF 70-30 refers to the final training and evaluation stage. I'm happy to say that both the random forest and neural network models achieved an OROC score of above 80% across all 5 datasets, i.e. above the threshold for success set out at the start of this project. and there was no overfitting. And here we can see the overall performance values from the earlier table visualized. As mentioned in the stakeholder presentation, feature importance was used to help generate insights and also prepare for future iterations of the project via feature selection. Using a cutoff threshold of 4% for average feature importance, 13 features were selected to move on to future iterations, i.e. those seen here in pink. These 13 features can be seen visualized here, and we can see how their relative importances shift year to year. And so finally, in terms of next steps, there are two that I've somewhat alluded to earlier. Firstly, now that we have down selected to 13 final features, my aim is to refactor my code for Python 3.9 plus to be able to spin up a stronger parallelized environment to train and tune the random forest models. The removal of noisy features should, in theory, further increase performance. Secondly, in conjunction with the reduced set of features, I would like to use embedding layers to allow the NN perceptron model to be able to more effectively and efficiently handle high cardinality categorical features. Embedding would allow these features to be encoded into a relatively smaller dimensional space compared to one-hot encoding, further increasing model performance by unlocking the predictive power of these features. And this brings us to the end of my presentation. Thank you for listening, everyone. As mentioned earlier, please feel free to add me on LinkedIn to connect, and all my files and resources for this project can be found in my GitHub for others to learn from as well. Thank you, Romeo, and the whole IBM team for a wonderful course. Take care, everyone.